Today we are going to build a small rig that will help us demonstrate operation of common electronic components. The rig will be powered from a 12 volts DC source and also from AC and square wave sources. LEDs, a light bulb, a motor and a speaker will act as load. A voltmeter and an ammeter will be used to perform measurements. This is Ron Matino. We've got our power sources on the left. This is a typical DC regulator. It allows you to adjust output voltage and is now set to 12 volts DC. This is an Arduino clone with MOSFET output stage. It's based on Atmega 168 MCU and can drive load using pulse width modulation. Output voltage and polarity can also be adjusted. By writing an Arduino sketch program, I was able to make it output AC and square wave. This output generates an almost perfect sine, while this one outputs square wave. The frequency can be set in the range from 1 to 50 Hz. Here's the source code of the sketch for your reference. If you have questions about the program, please ask them in the comments section. On the right, we have several types of load. This is just a regular red LED with a current-limiting resistor meant to be powered from 12 volts. This is a model of a speaker made up of 6 PC buzzers. This is a regular 12 volts rated light bulb. This is an electric motor salvaged from a CD-ROM spindle. And these are 2 LED lamps, white and yellow. They are connected in opposite polarity. This will help us better understand AC circuit's operation. And finally, on the top, we got our measuring instruments. These are the voltmeters, and this is the ammeter. Voltmeters are always connected in parallel to the circuit whose voltage you need to measure. In this case, the voltmeter displays voltage of the DC power source, which is 12 volts. The ammeter, on the other hand, is always connected in series with the circuit whose current you intend to measure. In this case, the ammeter shows current that flows through the light bulb powered by the 12 volts DC source. As we can see, the lamp draws about 370 milliamps. The motor draws 22 milliamps. Now let's see what we got here. The generator is powered by 12.6 volts DC. I am now setting it to run at maximum frequency, which is 50 Hz. We have around 9 volts AC on this output. But this one has around 14 volts. As we can see, the voltage differs. I will not explain what happened here, but would like to hear it from you. Please tell me why the multimeter shows voltage below the supply on this output and above the supply on this output. You can leave your answers in the comments section. And here's a little hint for you. This voltage is displayed correctly, while this measurement is erroneous. Also, these 2 voltages are tied by a known formula. Please tell me what it is. When we power a load from a DC source, the result is pretty much predictable. The speaker clicks, the bulb lights up, the motor rotates, and these 2 lamps light up in turns when changing polarity. Now let's use a square wave source set to a frequency of 1 Hz. The LED is flashing. This happens because the LED, just like any diode, conducts current only in one direction, and we got changing polarity here. The speaker also clicks when the polarity is changed. The incandescent lamp, however, lights up continuously because it doesn't care about the polarity. As for the DC electric motor, this is a standard commutator model where direction of rotation depends on the polarity of the power source. And over here, I think, the result is pretty much predictable. Now, what happens if we power our load from a sine source, the LED brightness changes smoothly as the current rises and falls. If we increase the frequency, the flashing becomes less noticeable to human eye. The light bulb behaves differently. When powered from a square source, it was lit constantly, and now it's flashing smoothly. Setting frequency to maximum, the lamp is lit, but its average brightness has now dropped a bit. And this will be a clue for the question that I asked a minute ago. The motor also changes rotation direction, but again, now it happens a bit more smoothly. If we raise the frequency, the motor will be stalled, because a commutator motor with a permanent magnet may not be powered from an AC source. Behavior of the two LED lamps, I think, is clear and does not require explanation. Our first test subjects will be switches. The switches can be basically divided into two main groups: latching and momentary. A momentary switch retains its state only while you hold it down. A latching switch memorizes its state. A changeover switch has three leads. Its middle lead, depending on the state, connects to either of the remaining leads. A toggle switch is only capable of closing and breaking the circuit, and is either in on or off state. Also, switches can be single pole or double pole. The poles are unconnected, but work in sync with each other. Momentary switches can be normally open and normally closed. A normally open switch is off by default and turns on when pressed. A normally closed switch, on the other hand, is on when untouched and turns off when depressed. Any changeover switch can be used to drive two loads. In one state, the LED is on. In another state, the lamp is on. A double-pole changeover switch has one more typical application. It's used to change polarity of the load. This is often used, for example, to drive power windows in your car. To do it, we supply power to the side leads and connect load to the central leads. Double-pole switches are also used in high-voltage AC circuits to break both neutral and phase lines. The purpose of such connection is user safety. Our next component is called the relay. A relay is nothing more but an electrically operated switch. Just like regular switches, relays can be single-pole and double-pole, changeover, and toggle types. The relay is different from a regular switch in that to change its state, you do not manipulate it, but apply power to its coil. When you do it, you can observe how the relay armature moves. Some relays can be powered both from DC and AC, and some only from DC. Apparently, our relay is not designed to operate on AC power. Relays are used where it is necessary to control a circuit by an independent low-power signal, or where several circuits must be controlled by one signal. You can also use relays to build some fun circuits. For example, if you wire the normally closed relay poles in series with its coil, you will get it to oscillate. This happens because once the coil is powered, the contacts disengage and cut the coil power supply. As the coil is unpowered, the circuit is restored and the cycle repeats. On the other hand, if you power the coil in series with the normally open poles, you will get a latch. If we wire a light bulb in parallel to the coil, we can observe how it works. Once we short the poles, the relay latches and keeps the load powered until we break the supply. You can also add a normally open and a normally closed momentary switches to this circuit and end up with a fun automated switch that can turn any load on and off by a single press of a button. Our next chapter is dedicated to batteries. A battery's main task is to output voltage. Thanks to voltage, as the circuit is closed, the current begins flowing through the wires, so the energy contained in the battery starts to energize the load. The voltages of batteries connected with opposite poles add up. The voltages of batteries connected with same poles subtract. At this very moment, a 12 volts lamp is powered from a 12 volts DC source. Let us connect a battery in series with this circuit and observe what happens to the lamp. We can see that the lamp illuminates brighter. And what will happen if we wire the battery's negative pole to the negative output of the power supply? We can see the lamp grow dimmer. The more batteries we connect in series, the more will the brightness of the lamp increase or decrease. What happens to the current when a new power supply is added to the circuit? Same pole connection, opposite pole connection. Apart from the voltage, every battery has one more important parameter, which is called capacity, and is measured in amp-hours or milliamp-hours. There's a slight problem with this particular quantity, however. Two batteries whose capacity is measured in amp-hours are only comparable if they output the same voltage. This happens because amp-hours rely solely on current that a certain battery can produce. Say you're in a hardware store shopping for a cordless drill. You see two models. The first one's battery is rated 14 volts, 3000 mAh, and the other one 18 volts, 3000 mAh. Although the mAh rating is seemingly the same for both batteries, the second one actually has a larger capacity because it can provide the same current at a higher voltage. So, to compare rechargeable batteries, always look for the watt-hour designation. Our next test subject is the resistor. The main function of a resistor in electronics is to decrease current in an electric circuit. Our light bulb, as usual, is powered by the 12-volt supply, but a resistor of 47 ohms is connected in series. We can see current at the ammeter, and the voltmeter shows voltage at the lamp. Let us now short the resistor and allow electric current to bypass it. Now we see that the light bulb is illuminated, the current has increased, and the voltage at the lamp is now 12 volts. The amount by which the current in the circuit is reduced depends on the resistance of the resistor. The lower the resistance, the higher the current. I have now connected another resistor in place of the previous one. It's rated at 10 watts, 27 ohms. As a result, the light bulb glows, the voltage is about 5 volts, and current is 256 milliamps. Resistors can be connected in parallel and in series. If connected in series, the resistance adds up. If connected in parallel, the resistance is reduced. The light bulb illuminates brighter, the current has also increased. The voltage is 7.8 volts. If you need to calculate resistance of a number of identical resistors connected in parallel, it's relatively easy. All you have to do is divide the resistance by their number. The serial connection, on the other hand, is characterized by dividing the voltage between two parts of the circuit proportionally to the resistance. The entire circuit voltage is 12 volts. The voltage at the 100K resistor is 8 volts. The voltage at the 51K resistor is 4 volts. This topology is very often used in electronics and is called voltage divider. The voltage divider can accurately convey the shape of the step-down signal and can be used both in DC and AC circuits. Variable resistors are also widely used in electronics. Resistance of such a component can be set within a certain range, which allows adjustment of current in a circuit. Our next component is diode. A diode is a semiconductor device through which current can flow only in one direction. A diode has two leads. They are called anode and cathode. They are also often called positive and negative based on the direction of current conducted by the diode. To test a diode, you have to switch your multimeter to the appropriate mode. The gray stripe is the cathode, the negative. 0.473 volts. Note that the multimeter here shows voltage drop on the diode and not its resistance. Let's see what's going on in the circuit now. The light bulb is illuminated, but the voltage across its leads is 11.2 volts. 0.8 volts drops on the diode. Let us short the diode. We can now see the light bulb is brighter, and its voltage is equal to the power supply. That's 12 volts. As we remember, the light bulb does not react to voltage polarity. It illuminates permanently from the square wave. But if wired in series with the diode, it starts to flash. The reason is because the diode conducts electric current only in one direction. If powered from a sine power source, we can see the lamp light up during one half wave only. Same happens here. Now only the white LED is illuminated. So using a diode, we can rectify AC or square wave and drive the load intended to be powered from DC. But if we use only a single diode as a rectifier, we can use only one half wave. The other one that is cut off by the diode is simply wasted. To solve this problem, in electronics they use a component called bridge rectifier. A bridge rectifier is made up of 4 diodes and has 4 leads. 2 of them are used to feed AC, the other 2 output pulse DC. The principle of operation of a diode bridge is very simple. During one half wave, current is flowing through these 2 diodes. As the input polarity changes, another half wave begins, current is flowing through these 2 diodes. It looks like the light bulb doesn't care if the current is rectified or not. But the motor is rotating as it should now, although it's powered by an AC source. The red LED is also illuminated without noticeable pulsation. The fact that we cannot see LED flicker does not mean that it's absent. This can be easily verified by lowering the frequency of the generator. The bridge does rectify AC. However, it cannot turn the sine wave into a straight line. So the flicker that we observe means that the voltage at the LED is fluctuating. This is where a component known as a capacitor comes to the rescue. Once we connect a capacitor in parallel to the bridge rectifier's output, the pulsations are gone. We can decrease the generator frequency, but even at 1 Hz, the capacitor eliminates pulsations and turns PTC into DC. In case of a motor, this leads to a significant increase in speed, because pulsations prevent it from spinning up. A capacitor is like a battery. If you charge it with DC, it will power the load for some time. When we wire a capacitor in parallel to bridge rectifier and the voltage at its output grows along with the half wave, once it is greater than the capacitor's voltage, the capacitor starts to charge. As the voltage reaches its peak value and starts to decrease, the diodes that used to charge the capacitor shut down. Now the voltage at the capacitor is greater than the voltage at the bridge's output, so it retains its charge. The quality of smoothing that capacitor provides directly depends on its capacitance and also the load connected. The capacitor is not a conductor, but it still can conduct current while it's charging or discharging. As soon as the voltage at the capacitor reaches the value same as the power supply, the current stops flowing. What this means is the capacitor cannot pass DC current. If we try to power a DC load with a capacitor connected in series, it will only be powered for a very short period of time. However, if the power supply polarity is constantly changing, like in AC, the capacitor will conduct. And yet one more component intended for AC conversion is called the transformer. The functions of the transformer are very simple. When you apply AC to the primary winding, you get AC at the secondary winding. The ratio of voltages on the primary and secondary windings is proportional to the number of turns on these windings. This means transformers can step up and step down voltage. At the same time, it is typical that the power during the transfer of energy through the transformer, based on its efficiency, is preserved. So if you, for example, have a transformer that steps down voltage by 10 times, in theory, the current at the secondary winding should be 10 times greater than that at the primary winding. Transformers cannot convert DC current. I found this transformer in my inventory. Its primary coil resistance is about 1K. The secondary coil resistance is around 1.5 ohms. We could try to use it to step up voltage. However, wiring the transformer directly to our rig's AC output is not safe, because the load will be too big for the MOSFET drivers. Instead, we can try to power our transformer with a pulse from a DC source and connect an LED bulb to its output. As we can see, the bulb is flashing, which means the secondary winding of the transformer outputs voltage around 300 volts. We can also observe that the flashes occur exactly when the circuit is closed. This is explained by the fact that energy is only transferred while the magnetic field inside the core is changing, increasing or decreasing. In a fraction of a second, the magnetic core is saturated, and energy is no longer transformed. There is one significant reason why the transformer still plays a key role in regulators and power supplies. Transformers' windings are electrically isolated from each other. We can measure the resistance of each winding, but at the same time, there is no circuit between them. This feature is called galvanic isolation in electronics, that is, transfer of energy without direct electrical contact. The main purpose of that is user safety. Devices with internal converters that are not intended to be in direct contact with the user, like LED bulb for example, do not use transformers. We have finally made it to the main character of our story, the transistor. A transistor is a semiconductor device that is used to switch a load using an external control. A transistor has three leads: emitter, collector, and base. Transistor is connected in series with the load, just like a resistor or a switch. However, you may not connect it in any polarity. Since it is a semiconductor, it only passes current in one direction. The arrow of the emitter shows the direction of current flow. There are P-type and N-type transistors, also called the PNP and NPN. The difference between them is in the direction of flow of electric current. There are several ways to connect a transistor in your circuit based on what you're trying to achieve. The most common topology is the common emitter. If we're talking about an NPN transistor, emitter is connected to the negative power rail, the load is connected to the collector and positive power rail, and the control signal is fed to the base relative to the common, that is negative power rail. Without delving into theory, let's analyze all this with a specific example. Here's our first transistor circuit. Its diagram you can see on the screen. We have an LED in series with the collector, and we also have a resistor between the collector and the base. I am touching points A and B with my fingers. As we can see, as I press them harder, the LED illuminates and current about 10 mA starts to flow through it. Here's what's it all about. Human body resistance is pretty large, about 400K. It's easy to calculate that if I wanted to power an LED from a 12-volt source with my body connected in series, the current would be too low to light up an LED or trigger the ammeter. However, when I am, using my body as a conductor, feed current to the base of the transistor, the signal gets amplified. So the current that the transistor outputs on its collector, in this particular case, is 25 times more than the current passing through my body. And by the way, we have just built a device that is called in electronics a touch sensor, which is a kind of a virtual button that is triggered by touch of a finger. Please note that any devices that come into contact with the human body must be galvanically isolated from the mains network. If you've listened carefully, you probably noticed that between these three nodes we came up with a divider. The role of the lower arm is performed by a 680K resistor, while the upper arm is the human body. Obviously, I chose the 680K resistor so that its value is greater than resistance of my body, and whenever I touch points A and B, the voltage at the base of the transistor is more than half the supply voltage. Okay, I've built another circuit. Here we have a 6.8K resistor connected between the base and the positive power rail, which makes the transistor turn on by default. I have also attached a thermistor from the base to the ground rail. A thermistor is a resistor that is sensitive to temperature. There are two types of thermistors out there. Negative temperature coefficient NTC thermistors have less resistance at higher temperatures, while positive temperature coefficient PTC thermistors have more resistance at higher temperatures. This is the NTC thermistor. I am now heating it using a soldering fan. We can see the current that flows through the LED decrease, and its brightness goes down. As the fan is removed, the LED lights up. This experiment also illustrates the ability of a transistor to amplify weak signals. The resistance of this NTC thermistor is about 8K at room temperature. Although it's much less than the resistance of human body, we wouldn't be able to make the LED light up if we wired it in series with the thermistor. Please note that in our NTC experiment, we are using it to turn off the transistor, while in our body experiment, we turn it on. That means, if the sensor is wired between the base and the ground, the logic of the circuit is inversed. Our next component is the SCR, or the Thyristor. The SCR, just like a transistor, is a semiconductor device that's also used to switch load. But unlike a transistor, an SCR turns on instantly when a control signal is applied to its gate and remains in on state unless the power is removed, just like a toggle switch. For the SCR to turn off, it is necessary to cut the power supply. Using the normally open and normally closed buttons, we can build a latch similar to what we did with the relay. When control signal is applied to Thyristor's gate, it turns on. As the supply circuit is broken, it turns off. Because of Thyristor's ability to latch while energized and turn off when power is removed, it is mostly used in AC circuits. Such SCRs are called triacs. The triac is completely similar to the Thyristor, with the difference that it conducts electric current in both directions. The big advantage of using these devices for AC switching is that load disconnection is always phase-locked to the moment when the sine wave crosses zero, which significantly reduces interference from switching currents. Triacs, along with transistors, are widely used in solid-state relay circuitry. Now, I wired our SCR to the AC source, and the rest of the circuit, including the button and the light bulb, are the same. As we can see, the lamp does not remain switched on after button release, because with every half wave, the sign crosses zero, which turns off the triac. Triac's use in dimmers is based on the same characteristic. In dimmers, as the user rotates the knob, the control signal arrives sooner or later to the gate input of the triac, and at the end of the cycle, the triac always turns off. So, the later relative to the start of the cycle the load is turned on, the less power it will get, which will result in dimming. The last component we will be looking at today is the opto-coupler. Just like a transformer, the opto-coupler in electronics is used for galvanic isolation. However, unlike a transformer, it's only used for signal transmission, not to power a load. On the other hand, an opto-coupler can transmit both alternating and direct current, which a transformer cannot. Opto-couplers operate on the basis of light radiation. On the transmitting side, there is an LED, and on the receiving side, there is a photodiode or a phototransistor. So when you feed current to the internal LED of the opto-coupler, its light emission affects the receiving side, and information can be read from the output of the device. Some opto-couplers have a circuit at the output that simplifies further signal processing. For example, this particular one outputs TTL level signal and has an open collector output. In practice, an opto-coupler is used not only for galvanic isolation, but also for protection against interference. The most common example would be automotive electronics systems. If you try to power the processor that controls the ignition and the MOSFETs that directly switch the high-voltage coils from the same power source, the processor most likely will fail. For the same purpose, opto-couplers are often used in CNC machines. Since the light-emitting element of the opto-coupler is an LED, it cannot be powered directly. So, as usual, we must wire a resistor in series. Its resistance must be calculated based on the current found in opto-coupler's datasheet. To illustrate galvanic isolation, I feed the opto-coupler LED from an independent power source, the battery. The opto-coupler's internal circuit will be powered from our regular power source, whose voltage is set at 5 volts. As the power is fed to the input, we can see the yellow LED over here light up. And that would be it for today. If you find this video useful, please don't forget to comment, share and subscribe. And if you wish to drop me some Bitcoin or Ether, please use the links that you may find in the description. This was Juan Matino. See you next week.